Dear students, now we concentrate on Module 3 of Unit 4, which is related to the instruction level parallelism in the DSP chip. Okay, let me understand what is the instruction level parallelism and how to achieve it. Basically, to achieve the instruction level parallelism, we are using a technique which is called pipelining. So, let me understand what pipelining is. So in pipelining, each instruction execution is split up into a sequence of steps. So you just recall the execution of the instruction inside any microprocessor or microcontroller. For any instruction to be executed inside any microprocessor or microcontroller, several clock cycles are needed. And in if you recall that of 8085 or cross 86 family, the instructions need variable number of clock cycle, depends on the complexity, and the execution of the instruction involves several steps. So here the each instruction execution is split up into a sequence of steps, and different steps can be executed concurrently, means parallelly by different circuitry. Processor speedup can be enhanced by having separate hardware units for different functional units with buffers between the successive units. So here the circuitries are made in such a way that these units are connected in, you can say, stage serially, and there is a buffer between each successive unit. But all the units can operate independently and in the parallel. We will see in the picture in the next slide how it done. So the number of unit operations into which the instruction cycle of a processor can be divided for this purpose defines the number of stages in the pipeline. So we have the finite number of stages of the pipeline depends on the number of unit operations into which we are dividing the execution. So a processor having n stage pipeline would have up to n instructions simultaneously being processed by different functional units of the processor. And effective processor speed increases ideally by a factor equal to the number of pipelining stages. In DSP with Harvard architecture that we have seen in the previous lecture, where data and instruction lie in separate memory space, that is program memory and data memory, that promotes the pipelining. So even in DSP processor and some microcontrollers, the pipelining is always there, and we speed up the execution. DSP algorithms are often repetitive, that also we have seen in the previous lecture, the convolution, correlation, FIR filtering, right? They are often repetitive but highly structured, making them well suited to multi-level pipelining. Let me see one example where we have a 4-stage pipeline. This is just an hypothetical picture. Let me have one processor where each instruction, say here we have taken 4 instructions, I1, I2, I3, I4. Each instruction has some tasks, say addition, subtraction, multiplication, or even moving the data, storing data, loading data, like that. Let me have 4 different kinds of instructions, say I1, I2, I3, I4, and we have a 4-stage of pipeline. So usually the first stage of pipelining is always fetch. F1 means fetch the instruction from the memory. The instruction is always stored in the program memory. So let me say fetch it from the program memory. The second stage is always D, which is called the decode stage. So once the instruction is fetched, that means its opcode or its hash code is fetched, and then it is decoded by the processor. And after decoding, the processor will come to know which kind of operation this instruction represents, like addition, subtraction, multiplication, moving data, storing, loading, or branching, like that. So after decode, the third stage is operate stage or perform operation. So if it is addition, perform addition between 2 registers or the data with memory, or subtraction or multiplication or moving data. So the third stage is perform operation. Now fourth stage is W1, means write the results. After getting the result of addition or subtraction or multiplication, the results are to be written into the particular register or particular memory location. This memory location may be here data memory location, right? So that fourth stage is W1. So that W corresponds to write results. So if we consider in hardware organization, it is like this. This is the hardware organization. 4 stages are connected in cascade or in serial, but have buffers or storage buffers between each successive stage. Say F, D, O, W, where this B1 is the buffer between F and D, B2 is the buffer between D and O, and B3 is the buffer between O and W. That buffer stores the outcome of the each stage. Okay. Now here we understand how this pipeline allows the parallel execution of instructions. So if we have I1 instruction is fetched at the first clock cycle, then the other stages, say D, O and W, are right now idle. When the processor comes to the second clock cycle, this instruction is already fetched, so now it will enter into the decode stage. But at this instant of time, this unit is free, it is vacant. So that unit is used to fetch the instruction I2, which is next to the I1 residing in the memory. So that next instruction is fetch. So it is indicated here, say F2, fetching of instruction 2. So these two are now going in parallel. Now at the third clock cycle, this is decoded. So now the processor say it is addition. So it will start addition in the third clock cycle indicated by O1. So that is perform operation. But now at that instant of time, this D and F stage are free, right? So now this instruction, second instruction I2, which is already fetched, will now enter into the decode stage, and the fetch stage is free, so it is now used to fetch the opcode, or you can say hash code, of the third instruction F3. So now these three operations are in parallel. At the fourth clock cycle, this I1 instructions operation is performed, say addition is performed. Let's say now store its results in memory, so that is done in the fourth clock cycle and by unit W, which writes the results. But at that instant of time, now the three stage O, D and F are free. So this second instruction, which is already decoded, now enter into the O2 stage, say it is multiplication. So multiplication get performed. This D stage is free, so that third instruction, which is already fetched, now enter into decode. Now the fourth instruction will get fetched in parallel. So now all four stages now working in parallel at the fourth clock cycle, and now onwards you can see at the fifth, sixth, seventh, all things are in parallel. So if we have a I5, I6, I7 after I4, then all four stages are now utilized and they will run in parallel and give us a throughput of one instruction per clock cycle, right? So at every clock cycle we get execution of one instruction. So that is the advantage of pipelining, right? If there is you can say no such structure, or you can say there is no pipelining, then if we operate this one by one, then each instruction takes here 4 clock cycle. So we get the execution of instruction only after 4 clock cycle. So this fourth stage of pipeline improves the operation by a factor of 4, because after third clock cycle we get one instruction execution for every clock cycle. So this is the main advantage of the clock cycle. And if we refer to our earlier statement, a processor having n stage pipeline would have up to n instructions simultaneously being processed by different functional units of the processor, and effective processor speed increases ideally by a factor equal to the number of pipelining stages. Here in our example it is 4 stages, so it is improved by a factor of 4. But again the word ideally, why this is, let me understand. So there are two problems, major problems which are hazardous to this pipeline structure. The first problem is called data dependency in pipelining. Now if we have two successive instructions, they are such that the second instruction depends on the final outcome of the first instruction. So now this instruction cannot be executed, or it will not give the final result until the final results of the first instruction get available. So if the input data for an instruction depend on the outcome of the previous instruction, the write cycle of the previous instruction has to be over before the operate cycle of the next instruction can start, right? Because the instruction can be fetched, decoded, but when it comes to the operate cycle, right, the results of the previous instruction get available, which is only available after the write cycle of the previous instruction. So that second will not get, you can say, executed, or it operate cycle cannot function. So the pipeline effectively becomes idle. So there is some, you can say, a bubble in the pipeline. The pipeline is waiting, right? It is, you can say, there is, you can say, a wait period for the pipeline, right? So the pipeline effectively idles through one instruction and creating a bubble in the pipeline. Now this bubble will not affect only the second instruction, but it will also affect the next instruction after it. Let me see how, by taking one example. So the pipeline effective idles through one instruction, creating a bubble in the pipeline which persists for several instructions. Let me see. Let me have one example where my first instruction is this. It is simply, we have A register, add 3 to it and store the result in A. So it is just add A with 3 and move the result into A register. And the instruction after it, I2, second instruction, is like this. Multiply A by 4 and store it in B register. Now here you can see the output of this is to be stored in A, and input also depends on A, right? So the first instruction outcome is available only after its W1 stage, W1 operation get over. And this instruction multiply the content of A by 4 only if A contains the final result of this instruction, right? So let me understand now in a pipeline stage. Say, let at clock cycle 1, this is my I1, so it is get fetched. Clock cycle 2, this instruction get decoded, okay. The processor able to know it is addition with 3. At this instant of time, this unit is free, so the second instruction, which is this, get fetched, there is no harm, right? Now when it comes here at this third clock cycle, this instruction get operated, so it will add A with 3. Still the result is only added 3 plus A at this instant. So at this instant, this second instruction get decoded, right? And if there is a third instruction after this, it get fetched. But now what happens at the fourth clock cycle? This available results in the buffer of this O stage is utilized by this W stage to write again into the E register, but that will happen only after end of this fourth clock cycle. So now this cannot use this operate stage. It cannot be here O2 because that needs the valid result which is to be stored in A, but that is available only after W1. So there is one bubble here which we can say one time period which is idle. So for one clock cycle, this stage of pipeline becomes idle. Now if this is idle, what about this here? This is fetched, but still the result of this D2 stage is in its buffer. It is not utilized by the O2. So we cannot move this fetched instruction for decoding into, you can say, D3 here. So this also gets idle. So all stages of pipeline here get idle, right? Now after this clock cycle W1, the result is available in A. So now this continued, right? If this continued, now this is already fetched, so this get decoded. If there is a fourth instruction, can it be fetched? Yes. And then all things work in parallel again if there is no such data dependency again. So if there is such data dependency comes, it introduces a bubble in the pipeline and that will reduce my throughput. Right here you can see at this instant it reduced the throughput because there is no W2 here, but W2 is here, so it is delayed by one clock cycle here, right? So this is the problem of the data dependency in pipelining. It is also called hazards in the pipeline. What is the solution? The solution is here compiler optimization. Now this what it means. So usually when we write the program for DSP, we are writing it in some you can say integrated development environment, IDE, right, which contains the editor, and then the program which is written in editor will get compiled by the compiler. It converts your, you can say, higher level language into the lower level language, which is a particular you can say language for the particular processor. So the compiler will optimize your code in such a way that the successive instruction will not have such data dependency. So you need smart compiler. So that is called the compiler optimization, and that is there in the modern compilers. So the compilers that we use for the DSP processor programming, one example is Code Composer Studio that we are using to program the Texas Instrument TI DSPs. that compilers are using such kind of optimization where they will ensure that the successive instructions will not have any data dependency. So that solves this kind of hazards or data dependency problem, and we'll have again a throughput of one instruction per clock cycle execution. There is a second problem in the pipelining, that is called branch dependency. The branch instructions are most hazardous to the pipeline. So what is branch instruction? The branch instruction is a jump or call, or we can say a conditional jump, where the jump depends on some conditions. A jump if carry, jump if no carry. So if carry flag is set, the jump is taken in case of jump if carry instruction. If carry flag is reset, the jump will not be taken. So branch may be taken, branch may not taken. In case of the simple jump instruction or unconditional jump instruction or branch instruction, the branch is always taken. But when the branch is taken, the execution sequence will change, because now you need to fetch the instruction from the newer address which is not in a sequence. The sequence of execution get disturbed. So that will also harmful to the pipelining. Let me understand how this will happen in case of the unconditional branch and also in case of the conditional branch. And in case of the conditional branch, there are two ways: branch is taken or branch is not taken. Let me understand all these three cases. So let I have again 4 stage of pipelining, and in pipeline let my branch instruction get entered, say F1. Okay, no problem. At this clock cycle it get decoded here now. Okay, at this instant of time this F stage is free, so the second instruction, which is after the branch instruction, which is in a sequence, get fetched, because our pipeline stages are working in parallel. So okay, no problem, this second instruction after this is get fetched. Now after this clock cycle, at the end of this clock cycle, the processor came to know that this is unconditional branch. This is unconditional branch. That means this fetched instruction is no longer useful, because it has to fetch instructions from some other location which depends on the address provided in this branch instruction. So after decode stage, that particular address is known. So now when this will, in the third clock cycle, when this enters into operate stage, here again this F2 is to be repeated, because now we have to refetch the instruction which is at the address provided by this unconditional branch. Say jump, so it's from some location, say 2000. So from that 2000 address, the new instruction is to be fetched, right? So this is to be get flushed. So whatever be the instruction which is next to the branch that is fetched by the, you can say, pipeline stage, is to be flushed, and new fetch operation is required here. So this is a wastage. This is here the wasted. Whatever we have done previously is now flushed, so it is wasted. Anyway, that when this will operate in when this is in O1, but this is not in a D2 here, but it will be F2. Now when this will enter into W1 stage, okay, now this will get decoded, and that will now work in parallel if there is no again branch instruction. Okay, so in that way this one clock cycle is get wasted here. One clock cycle time is wasted here. Let me see what happens if it is a conditional branch and the branch is taken now. So let me forget this now. Let me concentrate on this third. So we have F1. Okay, now we have D1 here. This instruction is decoded. It is conditional branch. Processor has started fetching the instruction which is next to this conditional branch in F2, right? Now after decode, it is known that it is a branch instruction, but the branch is taken or not, it is not known, because it is conditional branch. So the results are required to calculate, because jump if carry means it has to calculate whether carry flag is set or not set. So that is known only after end of the O1 stage. Now meanwhile the stages here are filled, so that is D2. So at the end of this O1, it is now known that yes, branch is to be taken, carry flag is set, so branch is to be taken. So now the processor has to refetch the instruction from the newer address. So again it has to refill this fetch stage from the newer location. So these two stages of the pipeline get flushed. So these two, you can say, clock cycle time is wasted. And now when this is in a W1, this will in a F2, and then it can work in a parallel. We enter in D2, O2, W2 like that. Now suppose after this O1, it has calculated the result, and the result says that no need to take the branch. So no need to take the branch means the instruction which is just after the conditional branch is to be executed, and that is already we have fetched. It is also decoded. So now only thing required is to operate the result or calculate the result. So now no harm here. So this will keep working. So there is no loss of any cycle time here. So here in conditional branch there are two cases. If branch is taken, then the fetch and decode stage need to be flushed. There is a wastage of 2 clock cycle time, and then again it will be fetched from the new address and the execution will get started. But if branch is not taken, there is no wastage of time. Now here the results are, you can say, very unpredictable, right? Because the branch is taken or branch is not taken, that depends on the conditions. So we cannot predict whether our throughput will be 1 clock cycle, 1 instruction per clock cycle or not, right? Here it will give some random throughput. So what is the solution? The solution is provided by one hardware unit, which is special unit, which is called branch prediction logic. So this unit, whenever the branch instruction will encountered at the fetch stage, this branch prediction logic activated, and this will predict, depends on the previous history, whether this branch will be taken or branch will not be taken. Actually, this branch prediction logic hardware unit introduced first time in a Pentium processor, and then subsequent processors are also using this branch prediction logic. So in some modern DSP processors also this branch prediction logic is used. So it is used in some high-end processors. So that branch prediction logic will prevent, you can say, predict whether the branch will taken or branch will not taken, depends on the previous history, and accordingly it will set this pipeline stage in such a way that we will save some cycle time. If you are interested, you can look for the branch prediction logic on internet, how it will work. We are not going in detail of the branch prediction logic unit here. Anyway, then second technique to achieve the instruction level parallelism is VLIW. What is VLIW? It is very long instruction word. So a technique for instruction level parallelism by executing instruction without dependency, and that is known at the compile time and in parallel. So compiler packs multiple independent operations into an instruction, and that results in simple hardware but complex compiler. Again, we are moving complexity into compiler, not in a hardware. The hardware is simple. So let me understand here. So most of the DSP processors, modern DSP processors, supports this VLIW, where the instruction word itself is very long, means it has multiple opcodes and multiple operands. Usually if you refer to a microcontroller instruction, say add R0 R1. So add is your opcode and R0 R1 operand. So usually instruction has only one opcode and one or two operands. Usually operands are not greater than say 2 in numbers, and opcode is always 1. But in the VLIW architecture DSP, the opcodes are multiple, means add, multiply, subtract, like 3 operations are there into one instruction, and opcodes are also multiple, say R0 R1 add, R2 R3 multiply, say R4 R5 divide, like that, right? So here is one example. Say we have, say, A B C D E F G register. So one instruction has addition of A B, store results in F. So there may be opcode operands like this. E and G are divided, store results in C. X and Y are logically ANDed and store the results in say some D register. Z and H multiply, store results in say some W register. And you can see in hardware there are some parallel processing units, right? There are parallel processing units which can take inputs from all these registers, say A, B, E, G, X, Y, Z, H, and provides the outputs in parallel, right? So this is the VLIW instruction, which has multiple opcode, multiple operands. The opcode are designed in such a way that it indicates multiple operations, and operands are also multiple. A, B, E, G, X, Y, Z, H, all are the operands inputs, and F, C, D, W, these are the outputs specified in the one instruction, right? So all these are specified in one instruction. So when this instruction get decoded, processor able to know that, oh, this is VLIW instruction, so it feeds all this data to all these parallel units, right? All these units have this arithmetic logic capability to perform the addition, division, multiplication, logic operations in parallel and provide the simultaneous outputs. And at the W stage, right, result stage, all these results are written in their respective registers or memory locations in parallel. So this is, you can say, one instruction level parallelism. So our TI DSP 6000 series, they are using VLIW architecture. I will introduce it later on, the Texas Instruments 6000 series, right? And there is one more parallelism which is called data level parallelism. Whatever we have seen previously is the instruction level parallelism. So instruction set is designed in such a way that we have seen in previous, that VLIW architecture as well as the pipeline, right? So hardware is designed in such a way that instructions are executed in parallel. Now we have data level parallelism. So the data level parallelism is achieved by SIMD. It is for single instruction multiple data. So here instruction is one, but that one instruction operates on multiple data. So here say add, but add A1 B1, A2 B2, A3 B3, A4 B4. So one instruction is only add, but add A1 and B1, add A2 and B2, add A3 and B3, and add A4 and B4. Operation is same, instruction is single, but on a multiple data, right? So the hardware inside this DSP processors has some parallel processing unit indicated by PU, and there is only single instruction, right, but operates on the multiple data. So here it is indicated like this data pool. Say it provides A1 B1 here, A2 B2, A3 B3, and A4 B4, right? And then all these are operates in parallel and produce the results in parallel. So here it is a technique for data level parallelism by employing a number of processing elements working in a parallel like this. One instruction allowed one to operate on many pieces of data simultaneously, means it is vectorization. So you can relate it with the matrix operation or vector operations in mathematics, where if I do a matrix addition, so many additions are done, say matrix A plus matrix B of 3 cross 3, then 9 additions are done, and these 9 additions if we do in parallel, then at one instant or in a one instant of time we have 9 addition results available. So this is called vectorization. So these are important to the optimization of audio visual data, since such processing involves a lot of data that can be operated on in parallel. So for audio video processing, this SIMD architecture is always there in most of the DSPs. In fact, this SIMD architecture also first introduced in Pentium processor with MMX extension, multimedia extensions. Earlier, the processors were not supporting multimedia, means audio video processing. Later on, that multimedia extension support is added with the Pentium processors. So in that, the SIMD concept was added. Now all the DSP processors always have to process on audio video or multimedia signals, so they always have this SIMD inside it. Then one more thing that we need to understand, low power architecture. Now if we have so many things run in parallel, so many things runs at high speed, there is always a question of power consumption, right? So if we have very high power consumption, then the applications using this kind of processors will not be suitable for the applications which are battery operated, because battery will get quickly drained, right? So for some applications it is not yet suitable, which is mostly battery operated. So how to achieve the low power consumption? One thing that is used is voltage scaling, because we know that the power consumption directly depends on the voltage. So reduce the VDD, which is the power supply to the microprocessor or microcontroller or DSP processor in our case, right? So reduce VDD. But if we reduce this VDD, right, the main power supply, usually all digital circuits operate on 5 volt, but the modern circuits are operate much below it, right? Now if we reduce this VDD, what is the problem? The problem is the noise, because if we lower this power supply voltage, the noise margin will get reduced, right? So in case of the, you can say when the noise is dominant, then in that case it will create a problem. So here you can say technique or solution, that the core inside the DSP. If you refer to the overall architecture, the processor or DSP processor chip has one core, and then there are so many peripherals around it. So the core is the most inner unit of the processor. So that will not be subjected to much noise, right? So it will not require much larger noise margin. So the core may use the lower voltage, say 0.8 volt instead of 5 volt, and the interfaces around it may use somewhat higher voltage. If interface is at the boundary, means it has to deal with the external device where the when there is a question of noise is always there, right? It is always subjected to the signals which are coming from outside world, so it may get noisy. So that most outer interface can operate at 5 volts, so there will be always be a good noise margin. If it is somewhat intermediate, it can operate at 3.3, and if it is inside, it can operate at 1.2. So the interfaces can operate at some you can see intermediate voltage like 1.2, 3.3, and if it is most exterior, it can operate at the 5 volt where it is connected to the external world and where the signals are noisy and we need the higher noise margins, right? The second way to achieve the low power consumption is by power management. Now DSP processor has so many core units and so many, you can say, peripherals or interface units. Every time all units are not in, you can say, function or not in operation. So turn off clock to the units which are right now not in operation. So we can say turn off clock when chip is not in use. So part of chip or even whole chip is not in a use, so turn off clock. So power consumption gets stopped, because we know that every digital circuits, when there is a clock arrived, right, it keeps on doing change in the state and the power get consumed. So if we turn off the clock, right, there will not be any power consumption by that particular chip. So that applies to the whole chip. If whole chip is idle, nothing is going on, turn off the clock to the whole chip. If there are some sub modules or some only interface of the chips are right now idle, then turn off the clock of that unit. So that power management is also a feature of the modern microcontrollers as well as DSP processor. Then obviously one thing is increasing the instructions per cycle. We have seen a pipeline ideally can give one instruction per clock cycle execution, but even we can go beyond it by using some technique, right? And then if we have a say throughput of 2 instruction per cycle or 4 instruction per cycle, and if we are happy with the 1 instruction per cycle, we can reduce the clock rate. Now what is the advantage of reducing clock rate? Because the power consumption is also depending on the frequency of the clock signal. If frequency is higher, the power consumption is higher, because the change of state is too frequent, very fast. So that will increase the power consumption. So if we lower the clock rate, then the power consumption get reduced. But in ordinary processor, if we reduce the clock rate, then the speed of the execution also get reduced. So if we have a pipeline structure, a sophisticated pipeline structure which gives me performance which is beyond 1 instruction per cycle, say 2 instruction per cycle, and if I will reduce the clock cycle, say its frequency divided by 2, then I can achieve some, you can say, reduction in the power consumption. So that technique is also used in the modern controllers and DSP chips. Move complexity into software. Instead of making the hardware units complex, obviously the complex hardware units will consume the complex hardware units consume obviously the higher power. So moving complexity into software, and that's we are doing. We have seen the smart compiler, right? VLIW is more suitable for low power architecture because the multiple data are accessed in parallel and single instruction will operate on that multiple data. So this VLIW architecture is utilized by all modern DSP processors. Too many functional units and too many transitions per clock cycle increase the power consumption. We have already discussed it. Now put multiple processors or cores on chip rather than lots of functional unit in one processor. So if you need a very sophisticated processor to have lots many functionality, so instead of increasing the functional units in one processor, increase the number of cores, and these cores can operate in parallel. You might have heard the name Core i3, Core i7, where there are so many processor cores which are operating in parallel. Instead of having one processor with so many functional units, let we have so many cores which are operating in parallel. So we can manage the power very easily. So whenever all the cores are required to work, we can turn the clock cycle of that on, and whenever we not required to operate all them in parallel, some of that units can be switched off, so power can be shaved. So such kind of things are used in the modern even microprocessor, microcontroller and DSP processors. So here we end our fourth module. In next video lecture, I will go to the finite precision arithmetic, where we will see a fixed point arithmetic and floating point arithmetic, and also I will introduce to some of the practical DSP chips, right? Hopefully you have enjoyed this lecture. Thank you.